Alright, in this video we are going to go through the first part of your notes on electron configurations. In the video that follows this, we'll talk about the second part. An electron configuration is the way that chemists arrange electrons around the nucleus of an atom. If you want to think of it as a mailing address for an electron, each individual electron has its own specific mailing address for any element, and we list them all out, and that tells us where all the electrons are most likely to be found for a specific atom. So there are three different ways of illustrating electron configurations. The longest but the most complete way is the the orbital configuration diagram. It can be called orbital configurations or orbital diagrams, and it shows how each electron is placed within each specific orbital for sublevel on an energy level. And we'll talk about what that means in a second. The electron configuration and the noble gas configurations are two ways that will be discussed in the next video. We aren't going to talk about those in this video. But the electron configuration doesn't show you the electron placement within the orbital, only the number of electrons within each sublevel, which can also be called a subshell. The noble gas configuration is the shortest way to illustrate the electron configuration, and it shows you the electrons placements for only the highest energy level orbitals in the highest energy level, which is called valence electrons. These electrons are the ones involved in bonding. They're either being shared in a covalent bond or transferred in an ionic bond. Alright, so our energy levels and sublevels. We have a bit of terminology right now. Let's change that pen color actually. I like blue. It's too thick. Blue and thin. Alright, get rid of that. Maybe. Alright, so energy levels. The energy level, it actually corresponds to the row number on your periodic table. So there are 7 different rows on the periodic table. They number from 1 through 7. So you will have electron configurations depending on the number of electrons within that particular atom that can go up to a 7 as far as energy levels. So these are typically numbers. And if you want to think of what's traditionally called the Bohr model of the atom, where the nucleus is in the middle, each energy level is one of those rings around the atom. However, it was discovered that the Bohr model wasn't the most accurate, and that was discovered with information found with the light equations and wave theory that we've already discussed. Within each energy level, there are multiple sublevels, and this Bohr model didn't explain for those changes in electron energy levels. So now we have this quantum model of the atom that does. So the sublevels aren't given numbers, they're actually given letters. The sublevels can be S, P, D, or F. And these sublevels actually indicate a shape where you have the highest probability of finding an electron. And the way of thinking about this isn't that the shape exists and the electron can't move out of the shape. It's that scientists can pinpoint the location of an electron, and over time, every time they find the location, they create a dot and another dot. And I can't write on the graphic apparently. But over a period of time, they keep plotting the electron's location, and for an electron that is said to be in the S sublevel, it creates a sphere shape. And that's where it's found most of the time. It's all a statistics probability, the highest likelihood of finding an electron. The P sublevel is a dumbbell shaped, and if you think of a three-dimensional XYZ axis, you can actually have this oriented 3 ways around the axis. It can be oriented around the X, the Y, or the Z axis. So there are actually 3 P sublevels. With D, it creates this shape, And I won't begin to try to explain it over a video, but it can have 5 different orientations around a 3D XYZ axis. The last shape that's not listed here is really complicated that these electrons form, and it can have 5 shapes. So the first electron configuration we're going to talk about is it's the orbital configuration. But before we do that, let's look at just our general periodic table for a second. And the energy levels along with the sublevels can all be put on to the periodic table. And it nicely shows you how each electron is oriented. So we've always looked at our periodic table, and as we go from one element to the next, to the next, to the next, talked about how a proton is being added. Well, since these are neutral atoms, every time you go from one box to the next, to the next, to the next, an electron is also being added. So our atomic number is technically the count of protons. For purposes of this, it's going to be the count of electrons, because these are all neutral atoms. So hydrogen has 1 electron. Its 1 electron is located in the 1s orbital. So it's in the first energy level, and it's in this s sublevel. If we add an electron, all of a sudden we're over to helium. Helium has 2 electrons. Its first electron is in the 1s orbital, and its second electron is also in the 1s orbital. If we move on to lithium, lithium has 3 electrons, and we always start back down at the beginning. Its first 2 electrons, one can fit here, one can fit here. They go in the 1s orbital, and the third one can't fit in that orbital. Each box can hold 1 electron if you want to look at your periodic table and thinking of it as a placeholder for electrons. So 1 electron, 2 electrons, 3 electrons. The third electron has to go here, and it's the 2s orbital. We're going to spend a lot more time in class helping you see the pattern for this, but for now let's just look at our main periodic table and section it off. These first 2 columns are the s sublevel. We're going to come back to these in a second. The last 6, 1, 2, 3, 4, 5, 6, are the p sublevel. Our transition metals are the d sublevel, and these guys are the f sublevel. So if you have a box that falls in here, it's filling an f sublevel. The energy level corresponds with the row of the periodic table, but the sections, the periodic table can be sectioned off that way. Alright, so let's clear this slide and go to the next one. So to draw an orbital configuration, you're going to want to keep that previous slide handy for now until you really learn to see the pattern. But to draw the orbital configuration for nitrogen, if you look on your periodic table, has 7 electrons. So we need to account for all 7 of those and their mailing address if you want to think of where we're most likely to be able to find them. So that's our first step. And electrons always fill in from the lowest energy level up. So that's the hydrogen block on your periodic table. The first electron, regardless of what element it is always going to go in hydrogen's spot, which is the first energy level, and it's a 1s. It's the s sublevel. So arrows mean electrons here, and we typically only draw half an arrowhead. So the first electron for nitrogen is going to go in the 1s spot. Each orbital can hold 2 electrons. So the second electron for nitrogen is also going to go in the 1s spot. So this 1 is our energy level. The S, or the letter, regardless of whether it's an S, a P, a D, or an F, indicates its sublevel, which is really its shape. And these lines, well, we call those orbitals. And we'll come back to that in a second, but let's just finish our example problem. So we've accounted for 1, 2 electrons. We have 7, so there's 5 more we need to account for. So we have our 2s orbital, if you look on the previous slide on the periodic table. And that's after you filled the first 2 electrons, you have to go to the 2s sublevel. That's the next one. And you can fit 2 electrons in the 2s sublevel. You'll notice there's 2 blocks. Now we have 3 more electrons to fill because we filled 4 of them. The last 3, if you look at spaces 5, 6, and 7 on your periodic table, or numbers 5, 6, and 7, all go in the 2p orbital. So we aren't going to fill this orbital, or this sublevel. There's 3 orbitals. Each one can hold 2 electrons, so the 2p sublevel can hold a total of 6 electrons. But we only have 3, so it's not going to be filled. So it matters how you put the electrons in with an orbital diagram, because electrons, they all have a negative charge. So they don't want to be in the same orbital level if there is space for them to spread out, because they're naturally going to repel each other. So you're not going to fill 2 electrons here and 1 electron here, because these 2 electrons want to spread out and be energy-wise as far away from each other as possible due to their both having a negative charge. So we're going to put 1 electron here, 1 electron here, and 1 electron here. If we had 8 electrons, that next electron would have to go in one of these orbitals. It doesn't really matter whether you put it here, here, or here. It has to go somewhere. So one of these orbitals will have 2 electrons in it, and the other 2 would only have 1 in it. But keep that in mind, that if you're doing an orbital diagram, you have to spread them out if there's space to keep the overall energy level as low as possible. Let's look at this chart, and this will be it for this video. So for our S sublevel, this is the sublevel that's in the shape of a sphere. There's only one way you can orient it around the X, Y, Z axes, so it only has 1 orbital. Each orbital can fit 2 electrons, so you can fit a total of 2 electrons in the S orbital, regardless of energy level. The first energy level, the second, the third, etc. The S sublevel only has 1 orbital that will always only fit 2 electrons. In your periodic table, as you look at that previous slide, that's true. The P sublevel, you can have 3 different orientations around a 3D axis. So you can have 3 orbitals. Each orbital still only fits 2 electrons, so you can fit a total of 6 electrons. D had 5 orientations, so it has 5 orbitals for a total of 10 electrons, and F has 7 orientations for a total of 14 electrons. In your periodic table, if you count the boxes for each different type of sublevel, each letter, you'll find that these correspond to how many boxes wide each sublevel is. For example, the P sublevel on your periodic table is 6 boxes wide to account for filling 6 electrons in 3 orbitals. Alright, and that is it for part 1 of periodic table, or of the electron configurations.